This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Okay, welcome to Design Safe Radio. If you've been watching for a while, you're used to seeing me on Zoom with weird, wacky backgrounds, but this is real for once. So super excited to be at the Oregon State University Hinsdale Wave Research Lab in beautiful Corvallis, Oregon, with my good friend Barbara Simpson. Wonderful to see you again.
Yes.
So really glad to be able to talk with Barb today. We've been colleagues for 5 years now or something, I think, since we met at that first summer institute.
Yeah. And I was still a student back then.
Oh
so,
my gosh.
yeah.
Wow.
Yeah.
So going to get into all of your background, but you're a structural engineer doing amazing things. Your test is in the wave lab back there in the wave basin,
yes,
which is pretty cool.
Yeah.
So we'll be talking about all of the goodness that you do. But you're a professor at Stanford now, so congratulations.
Thank you.
The great shift in career there. So welcome.
Thanks. Happy to be here.
So you've got a new award, a career award.
Yes.
Can you tell us a little bit about what that is for folks who aren't familiar with that program? And then what does that mean? So you've got a new appointment. You're assistant professor at Stanford. Can you give us a little background of kind of how you got here as a hazard engineer, and what does that career award mean for you?
Yeah, so the career award is actually a little bit of a different NSF grant because it's associated with both research and education. And so I pitched a research idea that I became really passionate about when I arrived at Oregon State back in 2018. And actually, it wasn't really in my field, and it was kind of one of those risky bets. I became really interested in accelerating our structural simulations using graphics processors. And I knew absolutely nothing about graphics processors at the time or parallel processing. And so I ended up actually taking quite a few courses just to sort of learn myself about parallel processing. And then that evolved into eventually what became my career proposal, which was then supplemented by an educational component that was really focusing on how to involve computation and really programming in the structural engineering discipline at in the classroom. And so a lot of our students, particularly those from underrepresented groups, they come into these analysis courses that have to rely on programming because they just can't be done by hand, or if they were to be done by hand, that would be extremely inefficient. So they come into these classes and they say, but I'm not a computer scientist, or I can't do programming, and there's this total there's this fear surrounding programming, and it becomes like, instead of a logic game or a skill, it becomes something unconquerable. And so a good portion of my career award was focused on that, how to address lack of confidence when it comes to programming and computation, specifically when it comes to structural engineering.
Wow. Okay, so you've got this awesome career award that's helping, hazard engineers that are getting into the field grapple the beast of Python and SQL and all the other things that make me have headaches. I'm very much there with your students of like, this is why I only have a bachelor's degree. I'm like, I am not a computer scientist, I'm not a programmer. I know enough to be conversationally dangerous, but enough to get me into big trouble.
Yeah.
So, but your research focuses more on more than just that programming piece. It's like, okay, what do we use that tool, that skill set for?
Yes.
And a lot of it has been on this really cool area of soil and structure and how those react to each other. And as we're finding out back here, fluid and structure interaction. So can you talk about how that relates and what that means and how that relates to your current research focus?
Well, so like many structural engineers, my background is in earthquake engineering, and that's where I conducted all of my PhD research. But then when I arrived at Oregon State, and luckily we have these facilities in our background, I started thinking more about fluid structure interaction, and then that led me to sort of think about interaction problems in general, which are extremely interesting because they're sort of on that line between disciplines. And so rather than it just being a structural analysis problem or even a mechanics type problem, suddenly you're saying, well, what happens when we have a structure interacting with, say, a fluid, where maybe the governing equations are a little bit different. And so for me, I was always interested in multidisciplinary research and how do you sort of broaden the applications that structural engineering can be applied to. And so when I started looking at fluid structure interaction, it became more of a question of, well, let's start out with bridges and tsunami loading, which is, still kind of in the realm of natural hazards engineering and research, which is where I got my degree in. But then let's start looking at just more like, for example, floating bodies in general. And so then I was lucky enough to be part of a Department of Energy grant where we started looking at floating offshore wind turbines. And so then
now we can turn the camera around and show you so this gantry here is part of your test rig.
Not that gantry. That one.
This one's something else.
That one's something else.
That one's something else. That's actually a different Department of Energy.
That's for a wave energy converter, not my project.
Different one. This one over here. So the triangular thing I'm pointing at there.
Yes.
Is part of your test, and then we've got the rest of it out there.
Yeah, the setup, and so, I mean, for those in the audience who are structural engineers, this is basically a forced oscillation test. So there's going to be an actuator set up on that frame, reacting with our specimen, and then we'll be able to look at more of the hydrodynamic coefficients in a sort of forced oscillation test. So very Chopra 101 for those in the structural engineering community.
And for those of us who barely remember fluid mechanics, let's see if I can translate. So it's...
Yeah, please translate for me, because I don't even know fluid.
Water moving back and forth, and
yes.
How do they interact with each other and with the water, and how do you characterize that in math?
Yes, basically, that was really good. I would say that's 99%, yes.
See, I can be conversationally dangerous about these things, but stick me actually with those Python equations, and I'm dead in the water.
No, that's perfect, yeah.
Cool. So you're working on the fundamental research itself, and then using this into your work with students of like, hey, this is why you want to do this. You get to do cool stuff for the rest of your career.
Yeah.
This is why you want to spend tens of hours figuring out how to do Jupyter notebooks in Python.
Yeah. That's extremely important, because I feel like we all get kind of lost in the methods and the analysis. And then really what we care about is how can we use it to better understand, in this case, floating offshore wind turbines, but it could be the built environment, it could be natural hazards. Like, at the end of the day, we're applying it to something that's very useful and is going to ultimately push us along in society.
Yeah.
Thanks for listening to today's episode of Design Safe Radio. This show is sponsored by the National Science Foundation, grant number 2129782. You can subscribe to Design Safe Radio on iTunes, Stitcher, or wherever you find your podcasts. Please leave us a review so that we can improve the show and also help others find our episodes in iTunes. Thanks for your feedback and support. We really appreciate it. You can find out more about NHERI at designsafe-ci.org, on Facebook at Design Safe Radio, or on Twitter at NHERI Design Safe.